So today, I thought we would look at a little bit of Git. So I'm going to be using my, and one thing I would encourage you to do is ask questions when something is not completely clear, because the most important thing with Git is to have the right mental model. And if you don't have that mental model, then things will end up being, if I can find that particular XKCD, things will end up being like this. You've seen my mastering Git presentation, you'll have seen this. All right, so this is not where we want to be. We do not want to just memorize a bunch of commands. What we'd like to have is a good mental model of how things work. So there's actually a book called Smarter, Faster, Better, which is a really good book. And it talks about why are some people able to perform at just like an astonishingly high level. And so they look at things like Sully, who landed the plane on the Hudson, right? So how was it that he was able to do that kind of thing? Whereas other people will see some conflicting dials and they crash their plane, right? So, and it all comes down to having the right mental models. So I will stop that share and I'm going to try, okay, let's see, share my whiteboard. Okay, so you see my horrible artwork right there. Okay, so there's a porcelain and then there is the plumbing. So nobody wants to do the plumbing, right? But it's necessary. So we're going to talk a little bit about the plumbing of Git first. So I don't know if you've ever heard this, but or heard this description of Git, but some people have described it either as a file system. So it could be, whoops, that's a bad place to put it. Or a key value database. I don't know if anybody's ever heard of that. Have you heard of those two terms before? Okay, so no. It's not either one of those things, but it has characters. Well, it's actually, it kind of is a key value database. So it turns out in Git, we have a few different types of objects that Git is going to be tracking. We have, so here, let me just say Git objects. So we have trees. And a tree is like a directory. So it's just one level of a directory. It has names and it has pointers to other objects. But it doesn't actually contain the objects, but those other objects could be other trees or they could be files, but we don't call them files in Git. We call them blobs. Sorry. Blobs. I am really bad at this, but hopefully I'll get better. And then finally, we have these commit things. There are other things in Git, but for right now, we'll just look at those three. Okay, so let's say we look at a specific case of working with Git. So here's our project. Our project has some root, and so maybe this is TCPA, right? And so it's got one tree. I'll call this the tree, the TCPA tree. And it'll have something like, it'll have TCPA. And then it's got some, 0xf1, 2, 3, whatever. That's the pointer. And then it's got maybe the UI. And that's 0 by, and I'm just making it 0 by to make it a hexadecimal number, but like 4, 6, 7, 1, whatever. Right, so, and this tree itself has some pointer that's associated with it. We call this the hash. And so this will be something like 0 by, I don't know, I'm just making stuff up now, ACE 1, 2, 3. So the tree itself just consists of this data. And so it's just got name and directory. And then this, it turns out, if you look at, there's another tree, I'll call this F1, 2, 3, and that has, BP off, maybe. So there should be an underscore there. And it's got other things in it as well. And maybe that goes to, I don't know, D279.
So
okay.
Each file in a a repository has its own pointer.
Yes.
Okay.
Yeah. So this tree links up to, or that pointer links up to this tree. And then BP auth, what that's going to point to is actually a blob. And this will be D279. I'm totally making up these hex numbers, right? And so that'll say something like, its contents will be import, I don't know, Flask. And so it's just, Git doesn't look at this as being like something that it parses. As far as Git's concerned, anything inside a blob is just a blob. It's a blob of data. I don't care what it is. It doesn't even know its own name, right? So blobs don't know what they're called. The only thing that knows what a blob's name is the tree that points to it. So this tree up here says, oh, well, the thing that I know as BP auth is referenced by this particular pointer. Okay, so does the idea of trees and blobs kind of make sense so far? Okay, so one of the things about all of these objects, trees and blobs, and we'll get to commits in a moment, is the point.
One second. The blobs are part of the trees.
No, the blobs are just files. They're the contents of files. So they're pointed to by the trees, but they don't know what tree that they're in, actually. They could be in multiple trees.
Okay. Yeah.
Doesn't really matter. They have no reference back to the tree that they're contained within.
But the tree contains the blobs.
The tree has a reference to the blobs. So it has this number stored in it, which we'll call the hash, or the SHA sometimes. I'll say why that's called the SHA in just a minute, but think of this as just the pointer or the ID of that blob.
Got it.
And so then it can look up that blob. And so it turns out that the whole thing, like all of Git is just these keys or these pointers. This is why we call this a key value database. So it's a key, and the value would be this tree object. This key will give you this tree object. This key will give you this blob object. Right? So as far as Git's concerned, it's pretty dumb. Right? It's storing these pieces of data along with some hash. Now we call it the hash because the way that they choose the identifier or these keys is pretty clever. You take the contents of, say, the file that you're wanting to store in Git, and you compute the SHA, the secure hashing algorithm. It's one of the ways that you can basically take the content of this and reduce it down to a 40 byte, I think, string of hexadecimal digits, right? So it's basically just takes all that content. So two different blobs will have two different hashes. They're not necessarily ordered in any way, so it's kind of a randomized string, but that's the way that you calculate what this ID is. So let's say I wanted to have a new version of this tree or say I make a change to this blob. So I'd have a different blob here, right? So blob, and this could be, I don't know, 1, 2, 3, 4. And so that one, instead of saying this, it says from Flask import, whatever. Okay. So it has to have a different ID because the content's changed. That's how we generate these keys. And so we call it sometimes the SHA because it's SHA. That's the kind of hash. We call it the hash. And a hash it's a reference to taking a lot of data and mixing it up kind of like a hash that you'd eat for breakfast into a smaller amount. And so it's always going to be reduced to this one number. Okay, so if you want to store blob 1, 2, 3, 4 in your tree, your tree is going to have to look like this. Or sorry, that shouldn't be blob, but it should be BP auth. And now this is 1, 2, 3, 4, right? Okay, so if you ever change that key in there, then the contents of this tree change, right? The key or the tree itself has different data being stored in it because the tree is just this file listing. And so that means that the tree itself gets a new hash. And this will maybe be D497. And then if that changes, then that means that this tree has to change as well. Okay, so now the TCPA is going to have to say D497, and that's pointing down here, right? Which means that this tree changes, and so now this is 0 by I don't know, bad one. I love that you can do things like that in hex and spell real words. Okay, so this is what happens when you change even just one little file. If Git is going to keep a reference of this, it's actually got to do a different blob, which means that the tree that contains that blob has to change. And if that tree changes, then every tree that it contains or that it has to change as well. Okay? So these are the things that Git is working with. This is kind of the low level of what's going on. I'm gonna glance at this and see if there's any questions on what we're doing here. And we're definitely down in the plumbing level here. Right, so any questions about trees and blobs?
So anytime a blob in a tree changes, the tree itself changes. And so it gets a new hash. So when you push a change, or actually when you just do a change in your you change a file, anything, it will record the hash then, or when you add it and commit it. I'm probably going ahead, but
well, yeah, that's a little bit ahead, but this is kind of the way that Git is looking at the world. So okay. So when you've got something in Git, if you've got a different, like even a single file change is going to result, if Git sees that change, then it's going to have to recalculate the tree and any trees that contain that tree all the way back up to the root.
Got it.
Okay. So that's trees and blobs. Sounds like I'm talking about things that are going to betray the country. Trees and blobs. So anyway, see if we can do a second page here. Okay, so now we've got commits. So what a commit has, so commits also have their own hashes. So I'll make this 4291. And so the commit has things like author, committer, date. Sorry about my writing there. It has the message. All these things are contained within the commit object. And then it also has, it has parents. So one or more parents. And it has a tree. So as far as this data goes, most of these are just text. Everything above this is text. And it just stores it almost like a blob. It's not a blob, but it's almost kind of like a blob. But the parents, these are going to be pointers. And the tree is going to be a pointer. So this could be something like 1112, if that's the parent. And the tree, sorry, if I go back the previous, my tree was going to be ace 123. Right? So this is, okay. So what happens, and so that tree, we know where that tree is going. You can just follow this number and ask Git to retrieve that tree for you, right?
So would a commit potentially have multiple trees? Or
no,
is it only
commits always have
multiple?
exactly one tree because that's the root of your repository. So it's always going to reference the highest level directory that's part of the repository.
Oh, okay.
Yeah, but that tree can reference other trees, right? So it's a nested, like logically it's nested, but it's really just these pointers. So it's technically possible in the way that they store the data that you could actually have a tree that references itself and you could like have infinite nesting of directories, but practically speaking, that never happens. Okay. So that's what commits look like. Now, when you actually say, well, I'm going to make some changes, and let's go back. Let's say you do make that change, going from this tree to this tree, right? So you're just making one little change in your blob. So what does Git actually do? Git takes this and it builds another commit. Okay. And we'll make this one maybe 1294. And so it's got all that author information that it picks up from your Git configuration. We won't really pay attention to that. So I'll just say, that's as we would expect it to be. Its parent is 4291. And its tree is, and I didn't remember that one. So that's, the bad one tree, right? The tree is bad one. Okay, so you can look at this parent is pointing back to this commit. And so this is what happens when you make a commit to Git. You give it a tree, and it knows what the parent is because it's whatever the current, like what was the last commit. It knows what the last commit is. And so it builds this commit out of your current, or out of this tree that you've created for it. And this is how it builds that commit object. Now, if you change anything in a commit, then this hash is going to have to change as well, right? Because the hash, again, it's content determined. So if I change something like the author or the committer or the message, then it would give me a new commit object because it can't use this. It can't use this ID. It's got to store it somewhere else.
Wait, why did the tree change though? If the parent is, the previous
because
one?
you changed the tree. So actually, I don't even know if I can.
Are you saying that that's what was intentionally
Yeah, the
changed?
change that you did, the thing that you're trying to commit was changing this one line of text, right? So you went from import Flask to from Flask import. That resulted in a brand new tree all the way back to the root. Okay?
Got it.
So this is how commits happen. And that's what's actually going on. So in Git, you're always adding these new objects, right? Git very rarely gets smaller. It almost never gets smaller. You have to do lots of work to make it get smaller. It's always trying to track more and more changes. So I said, you could have parents. It is actually possible to have a commit that references two parents. So that's when we do what we would call a merge. So that's saying, it's kind of making a note that I want this to be considered as a descendant of these two other commits. Now, you'll notice that there's nothing in Git where this tree has to have any relationship to this tree. There's no requirement that they do. So Git is not storing changes. Git never stores the changes between two versions. What it stores is a snapshot of your whole working directory. There are ways that, it has ways of making that efficient, but you should always think of that as it's storing a copy of everything you're working on every time you do a commit.
Yeah, and so trees are just created and then thrown away.
They're not thrown away. They're still referenced by the previous commit.
Okay. Oh.
Nothing gets deleted. Yeah.
Interesting. Okay.
Okay. So this is what's happening when we actually create our commits. Now, the method of creating, so that's that's understanding why do people call it a file system? Well, because the trees and the blobs, they kind of look like a file system. This is how file systems actually work. So in Linux, if you have a directory that's stored in what we call an inode, and the inode will just contain the file name and a reference to the inodes of all of the files that are within it. And that file name might actually be a directory name, and that would be referencing the inode that the other directory lives in. Files themselves also have inodes. Those things are more like blobs in Git, but it's still just referencing where do you go on the disk to find this thing? And I think the reason why it looks like a file system is because Linus Torvalds wrote it, and he's written file systems. So that was kind of what he knows. And so when you have a hammer, everything looks like a nail, right? So, but it's actually kind of a neat little way of building these things. So now I want to talk about what actually happens practically. So when you are, so that's a little bit of the plumbing. But I want to talk about three different areas that Git knows about. So there is your working directory. This is the files that you're editing, right? There's also what we call the staging area. Sometimes it's also called the cache. And then there's the repository. So kind of have to have these areas. This will help you if you keep in mind that there are always 3 areas. So looked like Dustin was about to ask a question. Maybe not. Oh, okay. So the working directory, this is what you already are used to, right? It's files. You've got files, you're making changes to them. You're not using Git at all. You're just messing with files in a directory, right? So nothing is special about this. But occasionally you'll do something like git add, foo. What that means is take foo and look at it and put it into the staging area. So it's taking the current state of foo, and what you should think of the staging area is it's a commit that you're building, right? So it's a work in progress for the next commit. So a lot of the time what we'll do is we'll say something like, I don't know if you've used this command, but git add dot. That means add the current directory and everything below it to the staging area. And so what Git does at that point is it says, well, what's the current status of the repository? It compares it with the working directory, finds, basically just makes a snapshot of, well, actually, let me take that back. It doesn't really compare it. It doesn't really even look at the repository. It doesn't need to. What it does is it builds up that, the sets of all the trees and the blobs and everything, and it puts that into the staging area. So this is where it has that partial commit. When you actually commit, what that does is it takes the cache and it puts in the repository. So git commit fills in all of those extra fields, author, committer, date, message, and it will then move that object into the repository and it clears out your cache or your staging area. Okay? Sometimes we say git commit -a, and that does this. Kind of. So I don't necessarily recommend using that. Does anyone use that particular command?
Rarely.
Okay. So what that means is look in my working directory for anything that you already know about. So something that's from the repository that has changed. And if something's changed, go ahead and add it and commit. So it kind of does 2 steps. Now, this is somewhat smart, but it's not perfectly smart. So if there's something that is a new file, it won't add it to your staging area, right? You have to tell Git about the things that you want to be in that staging area. Okay, so that's committing, and that's kind of how that committing works. Does that make sense, having these 3 areas here?
Yes.
Okay. And I'm kind of winging it on some of this. I know that I've got good materials on teaching Git, but I'm also trying to compress them all into an hour here. So, so now let's talk about branches. So we've talked about trees, we talked about blobs. Now we're going to kind of simplify this. We're not going to look so much at the way that the objects work with each other. We'll just look at commits as little circles. And so if I've got C1, C2, and I'll say C3 here. So if these were committed in order, C1 to C2 to C3, in order to draw arrows here, referring to how Git is storing these, how would you draw those? Would you go C1 to C2 or C2 to C1?
C2 to C1.
Yeah, C2 to C1.
Yeah, because they always remember their
backwards.
parents, but they don't remember their children. Like there's nothing and in fact they can't remember their children, right? If I were to store the child of C1 in C1, C1 would change. And if it changes, then it would have to get a new ID. And that would mean that its parent had to get a new ID, and so on. So you only store your children, never you only store your parents, never your children. Okay? So when you commit, there is this thing called the head. And head normally is pointing to an object inside Git called a branch. And so we'll just say that this is pointing to the trunk. And trunk is not really, it's not an object within Git. What it is it's just a bookmark for a commit. So it's just storing the ID of that last commit. So what happens when I make a commit? I got C4 here, right? Once I do that commit, Git looks at the head thing. And that, again, that's just it's just something that's in your local repository, your local checkout, where it knows what the head is. It says, what's the current branch? And so that's really what head is pointing to. So the current branch is trunk. It says, okay, since you're on a branch here, what I'm going to do is I'm going to move this to point there. And so it's really saying head is trunk, which is C4. And that's how things move. The current branch is whatever head is pointing to.
Wait, so what moved trunk? Just the commit of C4?
And that's just a local thing, right? So this is what Git does is it updates. There's a text file actually inside your Git repository, which has the name trunk in it. Actually, it might. Let's actually look at that and see if. Let me see if I can share that instead. Okay. So let's actually look at this. So I'm in the TCPA repository. I'm going to make it a little bit bigger for you. So all of this stuff is happening inside the .git directory. So this is kind of interesting. So I said that there was a head. There's your head. What's head? It says, oh, well, that's a reference to refs heads RC auth. Okay, well, what's that? Inside branches. Sorry. Where isn't it? Okay, I guess it's not storing inside branches. Where is it storing it? Well, I guess it's in refs. I got maybe branches is something older. So refs, sorry, not remotes. Heads, RC, auth. Okay, so that's a file. It's only 41 bytes though. What's in that file? It's the hash. All right, so the head contains the text. So actually, let me see. If we look at head, that is the ref. It means that it's this ref, and that just means a reference to a commit. In refs heads RC auth, refs heads RC auth is a reference to a commit. And I think it's git cat file, I think. Yeah. So let's see what the object type of this thing is. So let's see what that thing is right there. It's a commit. Okay, so let's see what's in there. The cat file is a plumbing command. So, and then I think I have to tell it. I have to tell it what it is to actually do it. Fiffle, yeah. So that's the commit object. And I told you it has a reference to the tree, the parent, the author, the committer, and then the message is down here. Right, so if I then say, well, let's see what's in that tree. Sorry, git cat file tree, and then I can actually do some of this. Let's see if I can abbreviate this. 70 FAE, that should be good. Okay, so that's in the tree. So it stores the tree in a binary format, so that's a little bit awkward. Trying to think of.
So if you are in a headless state, that means that is empty.
So let's try that. I was trying to get that to look nice. Okay, let me go back up. And what I'm going to do is I am going to, let's see, let me just stash that for a moment. We'll worry about what stashing is later. But if I do git log, what this is going to do is starting at the current commit, it starts walking up parents to find out what the parents are. So let's look at this commit right here. Okay, so I'll just copy that. And I can check out any kind of a ref. What checkout does is it makes the head point to that thing. So checkout changes the head. And when I change that, I get the detached head state, which sounds like a really scary thing to be, right? Your head has been detached. It's not good. So what that means is inside the Git directory, when we look at the head, it's just pointing to this commit. So if I made a new commit now, it's not going to move any branches. The branch pointers don't move along. It won't change any branches because I didn't say to check out a branch. I said to check out a particular commit. So let's look back at the, see if we can look back at the whiteboard. Okay, looks like that worked. So if I checked out a particular commit, what that's going to do, let me break up my eraser here for just a moment. Okay, so if I'm checking out, say, C3, what that does is it makes head point directly to C3. And it doesn't point here anymore. Trunk is still pointing here. So if I made another commit, so let's just change this and get rid of that. So now if I make another commit, what's going to happen? Well, head doesn't know to move any branches. And so if I have C5 here and I make that commit, what it's going to do is so C5, its parent will always be where it branched off of, right? And head will move, but trunk does not. So that's what detached head is. And that's why you want to be careful with detached heads. So let me see if I can delete some of this and move it a little bit. The trunk didn't move. My head has moved. And yeah, so trunk, come on. Okay, can't write there. Okay, there we go. Trunk is pointing here. So it's detached, meaning it's not going through a branch name anymore. And so if I do make these commits and then I try to push trunk, well, trunk hasn't changed anywhere. There's no name that I can get to this commit. There's no pointer to it anymore. It's kind of lost. So if I don't want to lose it, one of the things that I can do is I can create a branch. So let's say I checked out something and it was this, I just checked out a commit and I really want to retain this. I want to keep access to this. So I made a commit, maybe I made a few more commits. And then I want to say, well, I actually do want to keep this. And so what I would do is I would say git, see is it just git branch? And I'll say, work. And so what that does is it creates a new reference work, which points here, and it moves head to point to work instead. Okay.
Git branch work. Would that command actually put you on the branch?
Yes, so whatever head is pointing to is your current branch.
Yes.
So this is actually creating a branch. Git branch does that. One of the tricky things about Git is that there's a lot of commands that are dual purpose. And so you can actually also say git checkout with a certain option, which will create a branch. And so it's git checkout -b.
Yeah.
And that will create the branch as well and switch you to it. I think git branch might not actually set actually, you know what? I think git branch doesn't do this part. I think git branch leaves you in a detached head state, but it puts this work branch pointing there, and then you'd have to check it out. Yeah. And that's why there is this git checkout -b. So it'd be git branch work.
I've done that one before. I made the branch, but I'm not actually on it. So git checkout is actually easier because it puts you right on it.
Yes. Well, so if you just check out work, if work doesn't exist, it won't do anything.
-b. Yeah.
Yeah. So maybe I should make this. So this is blue here. That's what makes that link. Or you can choose to go green and do both of these at once with git checkout -b work, which is to check it out and create the branch work.
So if you're in a detached, if a headless state, that means that you're pointing to, your head is pointing to something that's not actually a branch.
That's right.
And so if you find a branch and you point it to that, you should not be in a headless state anymore, right?
That's right.
Okay.
So is it correct to say that the general solution, I guess, or just, the way to get out of a headless state is just to check out a branch? Is that as simple as what it is?
Yeah, so if we switch back over here and look at the code again, or look at the actual repo again, then it actually tells you what to do. You can look around, make experimental changes and commit them. You can discard any commits you make in this state without impacting any branches by switching back to a branch. If you want to create a new branch to retain commits you create, you may do so now or later by using the C with the switch command. Okay, irritatingly, they changed the name of the commands here. Git changes things for a while. So it's git switch dash C is what they're recommending that you do. And that will switch and create a branch. So the same thing as checkout. And if you get tired of seeing this big message, you can actually do a setting in your git config to tell it to stop bothering you. I don't recommend doing that.
But
it's good to know that you're in detached.
The messages help.
Yeah. Okay. So you can also switch back and forth to your previous checkout by just doing dash. So that switched back to my branch. If I do it again, I'm just flipping back and forth. I'm moving to the last place I was. So now I'm back into the area that I was looking at before. All right, so that's what's going on with detached heads, and that's how head is moving. So the only things that head can move are branches. And so that's what you'll find inside that refs heads directory. It's just branches that head can move. They're going to be local branches. Right? We haven't talked about anything using GitHub yet, right? It's all local to your machine. So now we have another thing that can happen, and this is still on the local machine. I'll switch back to my nice, pretty purple.
Sorry, I was just taking notes, but the git commit dash, that's open and any time to check out the last branch or commit you were on.
Sorry? Oh, git commit, yeah. Dash is just the previous checkout. Just go to the last thing that you checked out. CD works the same way in Linux, by the way.
What was it? Yeah. What was the command?
Git checkout dash. Like nothing else, just one dash. That just means check out the last thing that you had checked out. And so you can swap between two branches really quickly by just doing git checkout dash and go back and forth. And then CD works the same way in Linux as well. Okay, so what about if I had, let's say I'd been working for a while, so 1, 2, 3, 4 commits, and C1, C2, C3, C4. So, and then I decide I'm going to do some work, and all of these, well, this is trunk pointing here. These all point to each other, like that. Then I decide, well, I'm actually going to be doing some other work. So I'm going to make an RC branch here. So there's two branches pointing to the same commit. That's what when you do your checkout dash B. And then I actually commit, and I create a C5. And so that part we understand. What will happen to the head is that RC work will actually now point to C5 because the head is moving it. We lost Dustin. He said he might have to leave. So I'm not sure why that's there. Okay. So RC work moved over to the C5. And then maybe I make a few other commits here. So, C6, C7. And each time I make that commit, of course, it's going to move RC work. And so maybe if I draw these a little bit differently, I can erase them easier.
RC work is your new branch that you're working on.
That's right.
You branch off of C4.
Yes. That's just because that was the first commit that I made where it was different from what was on trunk. Okay. Now somewhere else, someone, and there's some method, and we can talk about that a little bit later, but somebody else has been doing other things. So they've got, maybe trunk has advanced somehow. So C8 is up here, sorry, I should make this a circle, C9, and those are also based off of C4, right? And so somehow trunk, is pointing here. So, whatever. Let's just do it like that. Okay, so trunk's up here, RC works down here, and I discover somehow my repository has these two branches and they've diverged. So the simplest thing that I can do is I can say, well, I want to merge these two together by creating a C10, which is somehow going to incorporate the changes of both C9 and C7. Okay?
Yeah.
This is what we call a merge commit. Now, Git is going to do some logic, and it's going to look at the trees and see where the trees differ, and even all the way down to individual blobs. And it's going to try to find out, can I do this safely? Right? Are the changes in different files? Are the changes maybe in different areas of a file? Like, are they far enough apart that I feel safe to merge those together? And it'll try to incorporate those. So it's actually looking at two different snapshots and building this merge commit. Sometimes that fails. Sometimes it finds out that you change the same file in C7 and C9, and you change the same area of the same file, but you did different changes. So that's what we call a merge conflict. And it won't actually create that commit until you've resolved that merge conflict somehow. So what it does is it gives you the files in your working directory. It puts in these things that look like this. It's got some text, and then 3 equal signs, and then more text, and then text like this. And so it's like, this is what C9 has. This is what C7 has. And then it's up to you to edit that file and then add it to C10. You're adding it then to the staging area so it can actually build that C10. So when you have a merge conflict and you're trying to create this C10 by merging these two branches together, that's what you're doing. You're actually just building that commit. You're showing it how to resolve these conflicts.
When you do that, it doesn't matter what editor you use to make those files.
No,
right?
It does not matter.
When you open it, that's still going to be there, whether it's a notepad or IDE.
That's right. So just think of it as it's given you the copy in your working directory. It's halfway built that commit for you. So everything that it could merge, it's already added to the staging area. The things that it couldn't merge, it leaves in your working directory as modified files, and then it's marked them as conflicted. So you have to do something to fix those conflicts before it will create this commit.
Gotcha.
And so you don't have to edit it. You could leave the conflict markers in there if you wanted to. That's a really bad idea. And yeah, that would break our code. But what you do have to do, though, is you have to tell Git that you've resolved it. And you do that by adding it to the staging area. So it wants to see all those conflicted files added. And then once everything's added, then you can make that commit. Now, when you make that commit, if let's say we're still on the work branch. So what will happen then is it will move RC work there. And so that's what happens when I do that. And the way that I would actually write this would be that last little thing is...
Would trunk also be moved to
Git
C10?
merge, no. Trunk. So what that means is I want to create a new merge commit, which is based on where I am currently and where trunk is pointing to currently. So when you say, you can actually say git merge and give it a whole list of things as well. So you can have more than two parents. There are awkward, like references to Utah that people sometimes make with that particular, historical Utah, put it that way. They've called it a Salt Lake City commit, indicating you could have more than two parents in a family. So anyway, I think more inclusively, people call them octopus merges. So if you ever wondered why GitHub's icon was the octocat, that's why. It's because Git supports these octopus merges. You can have multiple parents coming into one place. Most of the time, it'll be just two, right? So when you do this, remember, it's only ever changing the branch that you're on. It's never changing other branches in the repository. So if I wanted trunk to move here as well, I would have to switch head to trunk. And then if I actually, there's a command that I can do here. I can say git merge RC work. Sorry, RC work. Now, what Git's going to discover when this happens is that it doesn't need to do anything but move what trunk is pointing to. We call this a fast forward merge. So, yeah, going back here, that's a and it's because it sees that that's just a future commit on my timeline, right? That's one of my child commits. And so I don't need to do any work because that merge has already happened, right? And so the same thing would happen if we didn't even have C8 and C9. Let's say trunk was over here, and then we tried to merge trunk. Well, it would just fast forward it through all the changes, and now trunk is pointing here at the end. Okay? So does the fast forward versus a non-fast forward merge kind of make sense? You're muted, John. I don't know if you're trying to say something.
Sorry. Okay. No, I was taking notes. I just hadn't realized that you have to kind of merge both in order to do that. I thought merging just like moved both branches forward, but that's yeah, good to realize.
Yeah, so it's just moving it's moving the current branch that you're on. And so a practical workflow is that you might say this branch went on for a long time. I might create a few of these merge commits as I go. And maybe trunk is also merging. And so what I'm trying to do is make sure that I keep relatively up to date with trunk, but then I don't ever move trunk until I'm ready to this is ready to be the main line of development, right? I'm satisfied with my branch. That's when I go back and I merge my branch into the trunk. And that could create this merge commit as well. I guess you wouldn't necessarily create a merge commit. You would actually be creating merge commits every time you pull trunk in. That's really when you'd be doing that. Right?
So in our case, we have, let's say we have trunk and we have dev, and then we have all these other branches off of it that we create. So when we merge, we're merging our branch into dev to have that kind of cleaned up and working, and then eventually dev into trunk.
Right. So we might start. So say we've got trunk over here, and I think so. Trunk and dev. The idea of trunk is trunk doesn't change all that much. At least this is one workflow that you could use. Dev changes more frequently than trunk, right? So, and then you've got your actual work. So maybe I shouldn't be drawing these dots here. So I come in and I want to start working on something. So maybe dev and trunk are both pointing to the same commit. And so I come in with my work branch and I'm going to branch off of that, right? So I come down here and I'm going to make some commits. And I'm satisfied with it. And so what I'm going to do now is I want that stuff to go on to dev. So dev is, again, it's pointing up here to that same commit. So what happens is I commit I merge, I go on, I check out dev, and I merge my work. I merge my work branch here. And so that creates this commit right here, which is technically, here. So this is a little bit ugly, but let me actually clean this up, because let's assume, I kind of assume that we're starting from a completely bare repository, which is not really the case. Okay. So let's say dev and trunk are on different releases. Okay. So I do my commits here. And then when I'm ready, maybe somehow dev has also received some commits. Whenever I'm ready to merge my stuff onto dev, I will check out dev, and then I'll say git merge work. And that creates a commit on dev, which includes both the previous state of dev as well as the work branch. And then when Dustin's satisfied that dev is doing well, and I think it's Dustin is going to do all of these maybe, then Dustin makes a merge to trunk. Right? And at some point, this was created off of trunk maybe.
Right.
And so that's kind of the way that we're hoping that things will work if you're doing merging.
And trunk is most likely that's going to be what is deployed, what's actively out there.
Yes.
Got
That's
it.
correct. So, and I should have drawn my arrows the other way. I drew them in the wrong direction. It's hard to remember to draw them backwards. Okay, so one other thing, which I'll at least. Oh,
I have a question.
Okay.
So we typically aren't going to do kind of what you showed in that first scenario up top of merging both into trunk and into the working branch.
So
right?
so here's what you might do though. Let's say you branched off, you'd made a commit, and then someone else made a commit to dev, and you want those changes to be pulled into your stuff. So what is completely legitimate to do is to pull that into your branch. And so that would be on work, I say git merge dev, and that pulls that data in, creates a new merge commit here. Then you make whatever changes you wanted to make. So this is kind of keeping myself up to date as much as possible. And then when I'm ready to, when I'm done with my branch, then I might go onto dev and merge it there.
Yeah, but you're not going to merge the work as well and maintain, I guess, that branch.
Right. So work, this is going to be relatively short-lived, or that's the goal. We'll name this not work, but we'll name it like whatever feature I'm working on, like Home Depot or whatever. Usually we try to put our initials in the beginning of that.
I want to pause real quick and just show like a version of how we name things on the branches. Because it's not super important, but the inconsistent branch names triggers me.
Okay, so yeah, just
first know how we typically.
Yeah, so RC would be my prefix, Dustin's DN, John would be JJ, and Damien would be DJ. And if Amelia does any, it would be
Does it trigger you if mine are capital J's? Because for some reason that was happening for a while. I haven't seen if it's still.
Honestly, yes.
Yes. Okay. Okay.
It's stupid. It's just the inconsistency bugs me. And then the name of the branch is typically whatever feature or bug we're fixing. It's not just the client name. Because what ends up happening is all the branch names are the same, and I can't tell which one is which. I have to go look at commits.
Oh, got it.
Yeah, so it's fix auth, right? Or where. Whoops, I don't know what I just did there.
It's a selecting tool.
Yeah, how did I switch to the selecting tool? That's the real question. Okay. Where it hurts. And no. So yeah, so that would be kind of how we would want to do that. If we were really super careful about it, like if you wanted to have a really solid process, we could actually have the ticket number that we're working on incorporated into the branch name. We don't require that.
You might see that. I do that still out of habit in the commit messages, because we used to have Slack integration with Pivotal, where if I would put in like a number sign and then the ticket number, then it would put a link in Slack to the Pivotal ticket that got updated.
Yeah, we might do that at some point.
Yeah, we don't have that set up now, but that's why I put those numbers in there.
Okay, so one other thing that I'll just mention super briefly here, because we're already at an hour. You probably have run into this thing called rebasing. So what rebasing is, and again, everything that we're doing now still on local machine. We haven't even talked about how we could get other people committing to our local repository. But let's say we have, we've got the same sort of a process here. Okay. So I made my branch here. Things are happening on the existing trunk. Sorry, dev. And this is my work. RC work. Okay. Right. So what happens? So we've seen how I could, when I'm ready for this to all go back. Well, actually, we've seen how if I wanted to pull changes in from dev, I could do that by creating this merge commit. Right. But there's another way that I can get changes from dev. And that is to do what we call a rebase. So what a rebase does is, let's say, actually, I've done too many changes here. Let me erase some of these. Just do maybe just the one change. So I did my checkout, and I did a bunch of stuff, and then I realized that I really want this change to be included on my branch as well. Okay, so I could build a merge commit here, right? So that's one of my options. So I can merge all of that in. And that's a relatively short operation. All that does is going to compare these two trees. It's going to find any conflicts. You're going to resolve them. You're going to do a git add, and it creates the merge conflict. So that's option one. The second option is we can do a rebase, and that's what we tend to do more frequently. Okay, so what rebase does is it wants to build a new history. What it wants to do is build kind of an auxiliary tree here. That looks like this. And so this is, here, I'll give these names, C1, C2, C3, C4, and then this is green. This is C1 prime, C2 prime, C3 prime, and C4 prime. And it wants to do this in a way where it's almost as though I had already known about this when I built my whole branch. And so what it does is it goes back to C1 and it looks at what are the changes. This is where it actually starts thinking about what changed in different commits. So it's what were the changes between this commit and C1? Can I take those same changes and apply them to this? I don't know, I should call this like dev 0 and dev 1. Can I replay these changes on here? Right, so if look at these deltas, make the same deltas on D1, and if I don't get a conflict, it'll go ahead and create a C1 prime. And then it looks at C2 and it says, well, what were these changes? And I'll call this delta 1. Those are delta 1. This is delta 2. It tries to compute what the delta 2 would be if I made the same changes to C1 prime. Delta 3, delta 3, delta 4, delta 4. And if I can do that, then what it does is it replaces all of these branches, and then this becomes my new, this becomes what RC work is pointing to. And so the command for this is git rebase dev. And again, we're always changing the current branch. We're not changing dev when we do this. We're saying rebase this onto the current latest version of dev, or whatever dev is pointing to. And so it replays all these. Now, here's the tricky part about rebasing. I think that's, I don't think that that's too tricky. The most tricky part is what happens when there's a conflict in Delta 1. You might have experienced this. If you've got a whole bunch of commits that you want to rebase, and it gives you a conflict, we'll say, you gotta do the conflict resolution. And once you're done with conflict resolution, you add the conflicted files and it builds your C1 prime. And then you do git rebase -- continue, as it tells you in the nice long commit message, or the nice long error message. And if you had a conflict here, you'll probably have a conflict here as well. And so you fix the conflict there. And then it tries to apply Delta 3, and then you have a conflict there. And so at some point, it becomes too much effort to try to fix all these. So hopefully when you do this rebase, everything's fine, right? It doesn't run into conflicts. If you find that it's conflicting on every single commit and your rebase is taking forever, that's probably the point where you say, screw it, and you build a merge commit. Sometimes we'll call these bubbles in our commit history because they kind of look like bubbles, because we've got, down here I've got C5, which is a merge commit of this and that. That's kind of, I give up.
Alternative is you squash your commits into a single one, so you only have one merge conflict to resolve.
So that is,
one round.
Yeah, that is another option. There is actually a git rebase -i command. And what git rebase -i will do, and then you can give it like dev. What it does is it brings up an editor and it shows you all of your commits. So it'll show you C1 through C4. And you can choose on each one. It's got some instructions in there. It says, do you want to keep this commit? Do you want to delete it? If you just delete the row, then the commit completely goes away. Do you want to squash it? And that just means we want to combine it with the previous commit. Or do you want to call it just a fix-up commit, which means I'm going to squash it, but I don't care about changing the message. It was, maybe the message was nothing useful. It was just WIP or something like that.
Mm-hmm.
So when you choose to squash these, or I think is there a squash command, Dustin, that's a standalone as well? You're muted.
I don't know if there's a standalone command. I always just do the interactive rebase.
Yeah.
And I tend to be fixing more than squash.
You tend to what?
I do fix-ups more than squash. Because
yeah, the only difference
usually
between
I combine it all into a single commit and then reword the commit to include whatever I need to.
Okay, yeah, the only difference between fix-up and squash is that squash will take all of the commit messages and put them all in one text file for all the things you're squashing together, and then let you edit that. But that's rebasing. You can see it's doing a good bit of work by calculating all these deltas. Merging is a little bit easier, but that's kind of it in a nutshell. So things that we did not cover, we didn't talk about remotes, aka GitHub. We didn't talk about the stash. And I guess did not mention.
I got one question.
Okay.
When you said the other alternative is merge commit, is it just git merge, or is that the command merge commit?
Oh, it's just git merge. So you're on RC work and you say git merge D1.
Yeah.
Okay. And it creates C5. That's the I give up stage. If you really want to keep C1 through C4. Okay. Mm-hmm. So if you understand the model where these commits are going, how the commits are referring to each other, a little bit about how the trees and the blobs work, then I think adding on remotes is not too bad. Because remotes are basically their bookmarks for what some other repository has in its database. And so what you would see is that if I look at my remote, they call them remote branches. If I say, well, what are my remote branches? You'll see something like, well, origin says that dev is pointing to D0. Or maybe this is actually how it happened. Origin says that dev is pointing to D1 or D2 or like something like that. And so you can tell whether you've diverged from some other repository, and then push and pull will let us move objects between those two databases. But we can look at that later since we've been going for 70 minutes. So other things that are big missing things that I haven't talked about, Dustin? You know of any?
I don't think so.
Okay.
Maybe you could throw up SSH keys.
Oh yeah, setup. Setting up Git for the first time is kind of an intuitive process.
Like well, so we haven't done anything with remote objects, but yeah, SSH,
So using
HTTP, auth for GitHub.
Storing your login credentials and all that stuff.
Yeah.
If you need to do that.
Missing anything else here?
Well, a lot of it's going to be on GitHub, so that there'll be more questions on that. But actually, more when we get to GitHub, the repository, public and private, and that kind of thing, I struggle with getting it set up right. I kind of fumbled my way through, and it worked. And just happy, but I don't know. When we get to GitHub, then that'll probably cover all that stuff.
Yeah. Trying to think if there's anything else here. Oh, we didn't talk about tags. We don't use tags a whole lot. But tags are one more object that can be stored in a repository. So we looked at trees, we looked at blobs, we looked at commits. Tags are a fourth type of object. And you typically use tags for releasing, or like for marking something as a released version of software. They are not heads, so they don't move when you commit to a tag. They're just intended to be like a persistent bookmark of this version kind of forever. So you can delete them and recreate them, but think of them as like long-running bookmarks. So, and I'll say AKA the fourth object of Git. All right. So hopefully that was somewhat useful. Kind of going back through with portion of the plumbing, how do these trees actually get stored? And if you want to if you wanted to play around with this and do some examples, you could actually look at this and say, well, what happens if I change this file, but I don't change anything else in the tree? Well, it turns out you don't need to store the whole new tree. You only need to store the parts of the tree that changed. And so a commit doesn't always store your whole working directory. A commit will sometimes say, oh yeah, and this subdirectory and all of its descendants, they're the same as they were in the previous commit. So it just kind of automatically compresses it a little bit in that way.